Right. Hello, brave soldiers here, week 10. So nice to see however many of you are able to join us in person. To those of you on Panopto, welcome as well. Okay. It's the last week of the quarter. Man, winter quarter I know is always a short quarter, but this one especially with that weird start in January. Today we are going to talk about, we're going to have a little bit of a departure. We are going to talk not about the theory of computer science, but the physicality of how your code and how memory is managed within the device. This is my attempt at getting our brains starting to think about it. So you can go onto the poll everywhere now and upvote or add an answer, and I want to look at them because I assume they will be a good time. But here's the idea, all right? We are a chef. And we are cooking in some very fast-paced restaurant. Like, I don't know if any watched The Bear, but like that stresses me out. But that's the situation. There's a lot of shouting, and for some reason, every single human is called chef. So I need the freshest ingredients possible, as physically close to the area in which I am going to be cooking. And the reality is that I'm going to consume those ingredients. I need to replace those ingredients. Some of those ingredients are available at stores. Some of them have to be grown on trees. There's a lot of different things that we do as humans to bring the complexity of wherever these ingredients find themselves in nature as close as possible to the cook stove in the restaurant. So I'm going to pop over to the pullover. I feel like that's the way to do this. Let's see where we're thinking so far. What are some ways to keep these things possible? Oh, I should look at this. It's active, right? That's right. Sorry, hang on. Now you got to watch me do this, Shanann. There we go. Let's see. Okay, let's see. Use Mr. Meow Meow Magic. I will also say, today I told Mr. Meow Meow that the students are anxiously awaiting the final reveal of Mr. Meow Meow's secret identity. And you know what? I'm not going to lie. They were like, I don't know if they need to know. So I'll let you all decide how to navigate that. Let's see. Okay, let's see. Create a system to track what inventory they have and when that inventory was bought. Updating whenever they use some inventory. That sounds so similar to like a spices-related question almost on the final or on the midterm. Yes, I think the key to that, right, is that we have some idea of we're tracking when we use things. And that maybe, if we've used something recently, we probably need to refill that type of thing. That's something we're actively using. Shout out to this person, Fridge, who possibly knows where I'm already going with this analogy. But yeah, you could imagine it would be a huge waste of your time if you wanted to cook something in your restaurant and every single time you needed a fresh cut of meat, you had to drive out to the store, you bought a single steak, and then you drove back to your restaurant to cook it. So we have this thing called a refrigerator that's sort of like a mini store to store things we acquire elsewhere, further away, closer to where our kitchen is. So a fridge makes a big deal. That definitely is going to help us keep fresh ingredients closer to us. Use ChatGPT. You know what? Maybe in a couple years. Wouldn't be surprised. Ooh, regular delivery. Yes, it's almost as if it would be nice if there was somebody behind the scenes constantly keeping track of where everything is stored and moving it across the different layers close to us. I like that. There we go. We've got a lot of tracking systems. This one is probably true. Because I will admit I'm not the biggest reality show TV person, but when Gordon Ramsay goes into a failing restaurant and just says reasonable things to people, it's very satisfying. Amazing. I love it. So yeah, so starting to think about if the chef is the person doing things, then all of the different systems that need to build up in support of getting the chef the stuff they need at the right time and in the right place. And knowing that it might take a few different systems in order to move this complicated inventory through all the different layers from orchard to plate or whatever you want to call that. Okay. I'm going to reactivate that. Okay, we have a lot of announcements though. Let's talk about stuff. Okay, I finally went and connected the Gradescope stuff to Canvas. So now if you go to Canvas, it will have the different weights per assignment grouping, and it should show your scores that you see on Gradescope for everything that we've published the grades for on the Canvas. You could have done this, calculation yourself or whatever, but now it's officially in there. And the thing about it is, I will eventually make your GPA grades from the Canvas grades. There's like a bunch of rules that says I have to do it from there, not Gradescope, blah, blah, blah. So now is the time for you to go and double check that everything is the way that it's supposed to be. Now there's some exceptions. This is going to take me a little bit to clean it all up and have it exactly the way that we want it to look. So first of all, just so you know, we have not applied the late penalties yet, of which there's actually very few. Shout out to all of you. We do have a script that goes through and detects how many late days you've used, if you submitted something late after the late days, and we need to go in and sort of like apply those late penalties. So if you've submitted something late over your late days, your scores may drop, FYI. 2, the midterm resubmission grades. I just wanted to talk about them, and then I will make this all happen. So hopefully the midterm in-person grade, just like your final in-person grade, feels somewhat easy to understand, in that it's just like the grade we gave you when we first released it. The resubmission grade, what I'm going to do is, for everything that you press skip on, you are going to get the grade carried over from the in-person version. And if you got a lower grade on the resubmission thing, I'm going to go back and replace it with the original grade you got, so that you should never have a lower score on the resubmission than you had on the in-person. Once I do all of that magical calculation, then I will average the resubmission grade, which will be higher, with your original in-person grade, and that is your final grade. I just have to do a little bit more spreadsheet magic to make that happen. I will do the exact same thing with your final when we have the official grades for all that. Lecture participation also still needs to be posted, but that's one of those in the extra credit category. I'm trying to think if those are yes, I think those are all the things. So does anyone have any questions about grades at this moment in time? Yes, please. Yes, thank you. Okay, I did put the section participation grades on there. If you have at least 7 section participation points, which you could earn across the 8 sections of 2 through 9, then we will drop your lowest exercise score. I still need to do that. Obviously, since you still have exercises coming, I will do that kind of thing during finals week. And what I will do then is I will go in, and instead of having a number on your exercise, it'll turn into a little dash, which is Canvas's way of saying, don't grade this person for that thing. Great question. Other questions? Yes?
So is these grades in Canvas just for storage, or are they going to reflect your actual final grade?
So the grades that you see in Canvas, those are the ones I eventually use to make your GPA. So essentially I hit export on the Canvas grades, and then I do all the magic from percentages to GPAs in that context. So you want to make sure that it is correct on Canvas, pending those little exceptions that I just listed. But that's okay. We got 2 weeks to solve these things. Yeah?
And when will we receive the GPA grade?
Oh, after the quarter ends. Like the usual, whenever, your quarter ends, when you usually do those. Okay. Cool. Other grade-related questions? I will be making a lot of updates and all this sort of stuff, so if anything comes up, yes, please, there. No, I do not do that. So for Panopto recording, the percentage to promise GPA that I published in the syllabus, that is my promise to you. I will say to all of you, that is a under promise, because the last thing I want to do is tell you a GPA and then give you something lower than that. That number also tends to panic people because, like I said, it's an under promise. So you should know that the percentage to GPA transfer usually ends up being a bit higher than what I promised in the syllabus. Yes. Cool. Other questions? Okay. Please take a look if you have any questions, concerns. Even if I said it, I don't mind retelling it to you because I know this is complicated. And also, you should all know that your grade is yours. And if you are like, I don't know, maybe that regrade request didn't go the way that I wanted it to, or, oh, there's a 1-point mistake. I am never annoyed by discussing grades with you. Shoot an email to CSE 373-instructors. That's the best way. So then I have a note of the thing. Also, you are welcome to schedule one-on-one time with me if you want to chat about literally anything at this point. I put a bunch more time on my schedule for the rest of the week, so I'm happy to chat. What was I going to say? There was one more thing that I needed to do on the grades. Now my ADHD brain can't remember it. Well, we'll talk about it on Wednesday, apparently. It's that I will probably remember. What was it? Anyway. Also, FYI, so section this week, section 10, we call it TA's choice. And so some TAs have really cool and interesting research experience and different interests, and so they might be doing sort of special presentations. And some of the TAs just want to make themselves more available to you to help you finish P4. So we will publish a schedule of what's going to happen on Thursday, and you will notice a lot of your sections will turn into just open office hours, and some will turn into special topics. So keep an eye on the ed board. We'll publish that schedule in some time. Yeah, okay. Wonderful. All right, let's get into our topic for today, memory and locality. So as many of you remember, which is honestly my joy, I am not a CS major. I am an EE major. They changed the name of our department to ECE, but we are all kindred spirits if you are an ECE major. So I care a lot about memory and locality. And the most common question I get whenever people from this course want to talk to me about career stuff is how far behind am I going to be when I become a professional software engineer than all those CS majors? And I get to very delightfully tell you, not at all. I have been that person, and I have also managed many of those people. And in fact, unless people tell me their degree, I almost can never tell what their undergrad is in. It actually becomes kind of a fun little get to know you thing. My new joke whenever I go to work is hey, surprise, I don't have a CS degree. People think it's cute, it's charming. The reason, too, is because I learned a little bit of a different way of thinking about the computer. So when I was on the journey to get my technical job, I had to, spin a little bit. What am I particularly good at? And the thing I always talked about is I care a lot about the physicality. I care a lot about how software impacts the computer. Yeah, maybe I didn't get to take compilers and security, but I did know a lot about op-amps. So I'm going to condense down what I think is the most impactful physical stuff from the computer if you are going to continue on with your software journey. But also just know this is a little bit because Casey just likes EE stuff. And yeah, I threw some easy questions on exercise 7 about it. Cool. Okay. Also, I realized I had never mentioned this at any point in the course, and I had nowhere else to put this slide. Remember that the way that computer memory works is these things we call binary. What this really physically, literally is something in the computer called a transistor. A transistor is essentially like a light switch, but it is so gosh darn tiny, and it is automatically turned on or off as we let electricity flow through the semiconductor. And this little electron either crosses the cavern and lets electricity flow, or it doesn't. So it's just a bunch of off and on switches. If you go look at really old computers, like Harvard's Mark II, the first official electric computer, the reason they were an entire room size is because they used to use vacuum tubes as their on-off switches. So imagine if your transistor was physically this big, how big your computer would be. Now we have a transistor density that has defied all logic and understanding. So your computers are incredibly smart because transistors fit microscopically together and can be switched on and off so quickly. That means that now we can transmit bits of data so fast, it really is beyond what human brains can understand. But remember that absolutely every single thing a computer is doing, whether it's doing artificial intelligence cheating of my exam, or it's doing beautiful generative art, whatever, all of that breaks down somewhere to a light switch being flipped on and off. And so we need a programmatic way to think about how we organize and move all of this data around in the computer. And remember, what's really happening in the computer is electricity. It's literally electrons moving about on those boards. And up until now, we have just sort of assumed that electricity is in that like physics, intro series, frictionless, imaginary space. Everything just happens instantaneously, but that's not true. There are physical distances that these bits must cross. There are issues of loss and heat and things like that as this electricity moves through the physicality of your computer. So, how does that impact our coding? Take a look at these two methods, sum1 and sum2. As you can see, what they do is they take in parameters n and m and something called table that is a two-dimensional array. And one of them has an outer for loop based on n and an inner for loop based on m. And then it prints out the table. And then if you can see here, the other one is just the reverse. So this one prints out table at I and j. This one prints out j and I. So really the difference between these two things is as it's traveling through a two-dimensional array, one is going across each row and then down to the next row and then down to the next row, and the other one is going down a column and then up to the next column and up to the next column. So why don't you take a couple minutes, look at the code, discuss these three questions with the people around you. Go ahead, take like 2 minutes. All right, does any brave soul want to just tell us, what is the code doing? I kind of talked you through how it's navigating, but what is the code actually doing? Just a high-level summary. Yeah, sure.
It's running through the 2D array and combining all the ints into one.
Yes, absolutely. It's just summing everything up, creating one int out of many. So it's accessing each individual location of the array. Is there any difference in the output of what sum1 versus sum2 does? No, I agree. These things do the same exact thing. It's all just about the order in which they access each of those individual locations within the two-dimensional array. Okay, so does someone else want to tell us what is the big theta of these methods? Yeah, please. Yes, exactly. They both run in theta of n times m, which is essentially just the dimensions of the two-dimensional array here. They run in the exact same theta. So everything we've done in this class up until now should lead you to believe that these two things run at exactly the same time. Is that true? Does anybody want to advocate or tell me what they talked about? I'm very curious what you talked about for this question. Which method runs fastest? Yeah, sure. Any ideas? Yeah? Hmm. Ah. Yes, it definitely seems to have something to do with like the orientation of the array. Great thinking. What other sort of things do we think about in this context? Yeah.
So I just kind of thought of it like, let's say you're trying to figure out how many clothes you have in the dresser.
Mm-hmm.
If you pull the first drawer out, sum up how many things that takes less time than pull a drawer out, add one for like the far left, pull the next drawer out, pull the next drawer out. So you're pulling a certain amount of more drawers out with one of them.
Ah, yes. Okay, this is an interesting analogy. Imagine we are looking at like a dresser of multiple drawers, and we pull out the first drawer. It feels like it would be faster to like sum up everything in the first drawer before pulling out the second one. But that presupposes that it's like one thing represents a drawer, like everything in that is sort of collectively stored, and that separate drawers are maybe separated the way columns are separated, which might be the case. I don't know. I'm just being annoying. But great thinking, yes. Yeah.
Yeah, I think the reason it would work like the drawer analogy is because it's an array of arrays. You can't just like, if you want to go to like the second row down all the way on the right, you first need to go down on the left and then all the way over to the right because you have to access the actual array.
Yes. So if we think not of a two-dimensional array as a matrix, which is almost always how we draw it. Like if you took in two-dimensional arrays here in intro, we probably drew them as matrices. Everything seems equivalent. And frankly, from a theoretical standpoint, continue to think about 2D arrays that way. People will draw them as a matrix. But if we instead think about our wonderful like drawer analogy, we were reminded that two-dimensional arrays are arrays of arrays. So it's kind of like there is a little bit of like an outer wrapping and then an inner array that you got to get to. So maybe the drawer is like each of the inner arrays and the dresser is the outer array, something kind of like that. So yeah, maybe it matters if there's a little bit of a different access between that sort of inner storage and the outer grouping of the storages. So here is a graph. This is the time it took. Okay, I haven't rerun this graph on this new computer, but this was on my Surface Pro 7. If you can kind of see this blue line that barely lifts up above the x-axis is the time it takes to run sum1, which goes within each of the rows before it moves to the columns. So this one is the kind of situation where we've pulled out the drawer and we've looked at everything in the drawer. This angry orange explosion is what happens when you run sum2. How can these things, where I've only changed 2 characters, run so differently? That's what we're trying to solve for today. Okay, and hopefully I will give you answers as to why these things happen by the end of today. So, I think I maybe briefly flashed this at you at the beginning, but this is also another explanation as to why we don't just time code and I force you to do all that annoying big O analysis, because look at how much variation there is. This is the time it takes to add items into an array int list. This is for small values. This is for large values. This is contains across an array int list, a linked int list, an int search tree. And you can kind of see, but like, gosh darn it, if those spikes aren't really in the way for us to be able to tell what's the overall trend there. I'm also going to talk to you today about where the heck those spikes could be coming from. So this is why we don't just time things, and also why I've saved you from this complexity of the physicality of the computer until today. Okay, so up until now, remember when we were first doing the data model, like the code model, and I was like, okay, just count everything as 1. It's a println, it's 1. It's accessing an array, it's 1. We just counted everything. I was lying to you. All of those things actually take very different amounts of time. But the deltas in those differences are like partial millisecond differences. So on an individual basis, we're just like, let's just round everything to 1. But when we think about this over time, those like partial differences can add up because just straight up, sometimes accessing some memory is cheaper and easier than others. Not accessing every single index of every single array will take the same time. In fact, sometimes it takes vastly different amounts of time. That is one of the reasons for those spikes. What if that array is particularly expensive to get to? Also, sometimes accessing memory is just really slow. Sometimes the store that's closest to the restaurant is out of the thing that you need, and you have to drive to the further away store. Or maybe you're one of those crazy farm-to-table places, and you have to drive all the way out to the farm. Those things also exist and impact your computer in different ways. So, I was starting to talk about memory, but let's actually look at it. This is probably the memory that you're most familiar with. We call this the RAM. It stands for Random Access Memory. This is the thing that is storing what your computer is currently doing. I sort of think of this as like your waking consciousness, because this only works when your computer is turned on. And it's managing all of the programs in your machine. So whether you're playing Spotify and you've got like something, some YouTube video going, and maybe you've got like a Google Doc open and you've got your IntelliJ open, this piece of memory is just a bunch of sub-pieces of memory. Each of these little black chips are just little ways to store memory, which means inside of each of these black chips are those transistors that I talked about, as densely packed as possible. They are soldered, or more likely manufactured, onto these boards. And each of these little lines, those are conductive wires that send the electrons between all of these things. I know it kind of looks that way, but not often do people like actually stop and think, yes, like these lines on the board are literally sending the data back and forth between these massive things. Also, if you go look at your tasks, all of this stuff, if you ever see, you want to see your current tasks, like for example, let's say PowerPoint crashes and is unresponsive and you have to go and you have to kill it. So you open up your task manager and you see all of these things. This is what's happening in your RAM. It's kind of like a view into what your computer is currently thinking about. Technically, it's just a big array. That's why we're kind of always obsessed with arrays. Because computers are just really good at arrays because they themselves are just arrays. Because every single thing in a computer is technically just an array of a bit somewhere. And each of these black things are just one really big two-dimensional array. Each location in the array has an address in memory. Instead of like a single int, it's usually a hex value. And if you have a 64-bit computer, it's a 64-bit address. Because that means you can have that many more addresses, which means you can have that much more memory, as opposed to a 32-bit address. It's all just about how much active working memory your computer can function in. I don't mean to point fingers or nothing, but listen, my mother is a kind but slower moving human. And she is the quintessential 32-bit computer because, like, you can only ask her to remember 3 things at a time, okay? And that is it, right? Bless her. But that's really what this is about, is how many things can you remember at any given time? What's your working memory? Great, thank you. So this slide you have seen. Now we're taking a look inside of one of those little black chips on your RAM. And so each of those spaces in memory has its own, this is probably in binary, but again, because it's a larger number, it would be maybe in hexadecimal. These are the locations of memory, and whenever you use the keyword new as a Java programmer, what you are doing is you are asking your partner in crime, the operating system, to go into some magical place in memory and find you space to store what you need to store. You are the chef at your station, and you are like, somebody go to the store. And they theoretically run off and do it because, yes, chef, I don't know. So remember that the magic of arrays is that the computer understands arrays. It's so fundamentally based on arrays that if you say new int 3, it will give you a space in memory to fit exactly that in what we are going to refer to as contiguous memory. Versus if we do this in a linked list and we call the new keyword 3 separate times, it only knows how much space to partition every time you call new. And so if this is non-contiguous memory, where it's an object that has to jump around, the other thing to keep in mind is, I know I sort of have been talking about jumping around, but where is it jumping to? Where are all the different locations that I can store this memory? Now, contiguous makes sure that no matter where in memory your array is stored, it's always together. But in this linked list situation, it turns out there's actually a lot of different places that the operating system can place your object. This is my very high-level analogy of how computer architecture works. Yes, question?
Yes, in the previous slide,
Sure. Oops.
what is the advantage of taking linked list over array if it is consuming that memory? Like anyway, if they are separated or not separated does not matter. They are anyway taking a part of array. So what is the difference?
The short answer is, what's the advantage of a linked list over an array? Flexibility. It's probably more time expensive, it's probably more memory expensive, but it's a lot more flexible. And if you have to move things around or insert or shift or something like that, sometimes all of that shifting and moving is so much more costly, you'd rather have them as separate individual nodes you can move around. Good question. Yeah, sure.
Generally, I don't know if this is like too specific, but like, do you need nodes to like explain like how long your array is, or like what are the like properties of this node object? Like, would an array of 3 boxes actually be like 3 boxes and then one to say, oh, I'm done with the array, or like this is an integer array, so this is that, is that, or is it like it uses all the space perfectly? Or is that?
So it does depend a little bit on how the language you're working in compiles to your computer. So Java's compiler knows how to communicate to the operating system. I want exactly the space for 3 ints. That's great because Java is a compiled language. And so it can help work in wonderful partnership with the operating system in that way. Because what happens is we write it in Java, which I know this is going to sound offensive, but Java is essentially English. Java was not written for computers. It was written for your brains. Feels like a cruel joke, but it's true. And then the computer takes the Java and translates it down into something called assembly, and then further translates it down into machine code. And in those translations, that's where the like real minutia of, hey, where is the space in memory to store the pointer? Hey, does it like partition exactly this much space? Hey, does it give us a little bit extra in case you grow? Those kind of stuff. That's all figured out in those phases. But we're going to keep it a little bit in this theoretical phase. But if you want to get into it, look into the compiler about how it does that translation. Okay, let's talk about computer architecture. So there are multiple layers from the action that can store different pieces of data. So you are the chef. You are making things happen. If you are trying to make things happen as quickly as possible, you're probably staying as like tight to your station as you can, and you have the immediate like things you need as close by you, right? The CPU, that is the central processing unit, that's the brain of the computer. That is the thing that's doing the immediate calculations. It's just combining numbers, moving numbers from different buckets, so on and so forth. The RAM that I was talking about, look, it's layers removed from that brain. And part of that is because the RAM's actually really big. Like if I were to, hold up a RAM, it's probably about like this big. It's kind of like a candy bar, a little bit bigger than a candy bar. That's actually enormous compared to the CPU, which is like, maybe the size of a postage stamp. Also, we have to think about where we can place things so that they're not impacted by heat, because heat excites electrons. And if you excite the electron too much, what if it flips one of those switches? Suddenly you've transformed your data. So heat in the wrong place can totally warp or change your data. So we need to keep the memory in a different place from where things get really hot. And we also need to take into account that these little electrons are physically moving through the computer. And that's not frictionless. They are physically moving through things. It takes time. They travel at the speed of light, but that actually isn't instantaneous. So the CPU can typically store about just 32 bits of memory. And I like to think of that as like literally the space on your desk, like right at hand. The RAM, that's probably like 8 gigs. I have grown up in a time where that is an astronomical size. Like, I did not believe we would live in a time with computers with 8 gigs. Like, that is probably the size of the entire grocery store. But we need to separate those things. We need something in between that size so that we have some access to things more quickly. We can separate out things so they don't get hot, so on and so forth. So the things that sit between the CPU and the RAM are what we call the cache. You've probably heard that term. You know, sometimes people will be like, oh, did you clear out your cache? Or I think even sometimes our website, you have to do like a Control-Shift-R to see the updates because your web browser is caching things. Cache in general is just a term for like storing things locally, more closely related to you. But this is specifically the cache in your computer. So you typically have 2 different caches, an L1 and an L2 cache. The L1 cache is closest to the CPU. Maybe that's like the drawer in your desk. It's really close. It has 128 kilobytes generally, so it's a lot bigger than 32 bits, a lot bigger. And this is about how long it takes to get that stuff out of it. So, you know, it starts to take time. It's not free. And then we can go out to 2 megabits, even bigger. But look, now it takes 7 nanoseconds to get out to that. Maybe that's your refrigerator. Or maybe like the L1 cache is like the mini fridge in your office, and the L2 cache is like the refrigerator, the shared kitchen, something like that. You have to actually get up and go walk to it. But then look at this massive jump in time. It takes 100 nanoseconds to go all the way out to the RAM. And that's not even the furthest out we can go. We could go all the way out to what is commonly referred to as the disk. Depends on the machine you have, but if you have something that's like literally spinning in your computer, and it's usually like the extra hot part on your laptop right underneath you, the solid state drive is another option for these things. It can store up to like a terabyte of data, which is astronomical. It stores that data even when the power isn't on, but it is so far out there that it takes 8 million nanoseconds to get out there. That is like the equivalent of going out to the orchard, planting a seed, waiting for the tree to grow, waiting for the apple to drop down, and then you pick the apple and then you drive it all the way back to the chef. That's the order of magnitude and speed difference that it takes to get all the way out to the disk for a piece of data as opposed to something that's like in your mini fridge. Yeah, question? Great question. What do we store in the disk then? So typically what we store in the disk is stuff that's large and we need to save when the computer's not actively running. So anytime you make a Word document, all of your music, your pictures, your videos, all of the things that you probably think of your file storage, it's not usually stored in your RAM. It's stored initially in your disk. And then if you're running some program that touches it or uses it, a piece of it will get sliced up and pulled into your RAM for a temporary usage. In fact, that's how this works. So the operating system is constantly evaluating what it is you are asking it to find, deciding where to go find it, and then bringing it as physically close to the CPU as it can, and doing so in a way where it's trying to anticipate your needs. So the more memory a layer can store, the slower it is to get out there, which seems a fair trade, right? We're going to go all the way out to what we might call cold storage. That's a long trip. There better be a lot of stuff out there, right? Accessing the disk is crazy slow. Anytime you do file processing, that is massively slower than just doing like calculations in the program. Question?
Yeah, why can't we just make like the CPU register like 8 gigabytes of memory?
So we cannot make the CPU memory bigger because the time we need to manage is how quick it takes to do a single calculation. That's the clock timer. That actually dictates the single set time within your computer. So in order to keep that steady, we have to have already processed and found all of our data, and we just can't look within something as big as the RAM in such a consistent time. So we have these layers to like find something, categorize it, move it closer, so that by the time it gets to the CPU, it's like I don't have to think. It takes me the same amount of time to grab from right here every single time. But I don't know why Safeway keeps moving stuff. It takes me different amounts of time every time to find it in the grocery store. So it would be really silly if I had to like look within the grocery store right next to me every time. Yeah, question. Hardware-wise, what's the difference between SSD and RAM? So it does matter. I don't know a ton about this stuff, but like I said, the RAM only works when it has electrical current running through it. For example, on like the disks, what's actually happening is it's making little laser cuts on the disk, like it's permanently changing that thing to represent the ones and zeros. Once upon a time, us millennials used to do this thing called burn CDs, and that was literally like a laser cutting into that stuff to represent the different ones and zeros. That's a lot of time what's happening in the spinning state drive. And if you think of it too, even further back, it kind of looks like a record. The way a record works, right, is you have that needle, and every time it kind of hits a bump, it makes a noise. That's actually kind of what's happening in the solid spinning state drive. That's why it's spinning, because it's picking up all of that data. That's very different from the RAM that we showed you, where as soon as you put electrical current in it, it's like all those transistors start listening and waiting for things. So that's sort of some of the difference. I'm sure somebody knows even better than I, frankly, in this room, those pieces. Yeah, question? Ooh, okay, I'm just gonna straight up own I do not know the answer to that one, but I bet you somebody in here does know better than me about the difference between how we support the CPU being optimal from the GPU. But good questions to ask. I encourage you to Google these things. Okay, I didn't make these slides. My former head TA made these slides. Also, I don't live here anymore, so I feel like I could do this. But once upon a time, for many years, I used to live in that building right across from the Safeway, like right next to Itadeki Masu. You know what I'm talking about? Anyway, I used to live there, and I was right across the street from the Safeway, and I would always joke that I'm like really bad at grocery shopping because I lived across from Safeway, so I would go get stuff all the time. And this is my cat, Iron Fist No Mercy. She usually makes a lot of appearances on Zoom. And so let's imagine that Iron Fist No Mercy needs her snacks, which she does, frankly. She is aptly named. She could, like her irresponsible mom, go to Safeway constantly to get her snacks every single time she does. But instead, that seems silly. What can we do to improve this? If we get a refrigerator, shout out to whoever put that on the chef one and upvoted it. Now, when Mercy goes to the store, to reduce the number of trips out to the store, instead of buying one fish at a time, she's going to try and buy as many fish as she can carry in her hand and take them all with her to reduce the number of trips to the store. Because now she has somewhere to store things closer to where she intends to eat them. This is the idea of a cache. A cache is essentially just a refrigerator where your operating system is going out to the RAM, aka the grocery store. It's picking up as much stuff as it can fit in one trip. Like, let's be real. Do you carry all the bags up from the car in one go until your fingers like burn and bleed because you are not making 2 trips to the car? Yes, you do. I've even seen those stupid infomercials where you can buy like plastic devices to make it easier to carry your grocery bags in. I'm not walking up and down the stairs twice. I'm going to maximize as much as I can carry in one go. There we go. Great. Okay. Yes, we love it. Okay, thank you. So that idea of trying to fill up the refrigerator with every journey out to get supplies, that is actually something we are going to call spatial locality. And the way that it works for the arrays is that when I go out to the data grocery store to get one item from an index of an array, I see the whole array stored together, and I think to myself as an operating system, well, if they want one index of the array, they're probably going to want another index of the array, so I might as well bring the whole gosh darn thing. It's like I got to drive out there anyway. Wouldn't it be silly if I just bought one apple and put it in an otherwise empty trunk? Better fill up that trunk, right? Spatial locality is the idea that when I access one location in memory of contiguous memory, I'm going to take the whole thing because I'm assuming if you access one index of the array, you're likely going to access other indices of that array very shortly. That's the other magic of contiguous memory. The computer sort of knows that memory is associated with each other. So when it moves it through the different layers of the memory architecture, it moves it together. There's another type of optimization called temporal locality. Temporal locality is the idea that those caches can only be so big, right? And so as we add things to a cache, we got to evict stuff. Well, what do we evict? We are going to evict things in the reverse time in which you accessed it, meaning you keep the stuff you used most recently and you spit out the stuff that you've taken the longest time to touch. I think I have a good slide. That's spatial locality. Here we go. Temporal locality. So the way that I kind of think of this, because also I'm a terrible adult, is you know how like you start to wear like your hoodies or like maybe your jeans, and like maybe you don't wash those every single time, so they just kind of start to collect on that like chair in your room because you're like, I'm gonna wear this like again pretty soon. Like I'm not gonna put it all the way away, right? But like that time that you got out the like rain boots or whatever, that goes in like cold storage, right? Like I use those once a year to go to the pumpkin patch and then I put them right back because I don't touch them. Temporal locality, temp being about time, is we keep the stuff we've used most recently as close to the CPU and we push out the stuff we've used least recently. Again, if we're keeping our refrigerator analogy, if I open up my refrigerator and I have a piece of cake in there that I'm eating like a little bite of every day, I keep that, but that weird gross stuff that my partner refuses to clean and hasn't touched in months, that goes first. That we throw out. So spatial is the idea that if I'm going to go all the way to the store, I got to fill up the car for every single trip, make every trip count as much as possible. And temporal locality is when I have to evict stuff from the cache, keep the stuff I've used most recently. Questions on those two optimizations? Yeah. Great question. The cache knows what you've used most recently, like somebody else put in our wonderful warm-up, is the operating system's actually keeping track. The operating system has its own like memory inventory, and it knows all of your most recent memory requests. And so if you, for example, accessed an index of an array, it will know like, hey, keep that whole array around because like maybe they're going to use that again. So the operating system's managing all of this for you. And everything we've talked about today technically has nothing to do with your code. The operating system's doing it for you. But, oh my God, I'm going to make this work time-wise. Amazing. Hopefully now, what is the difference between iterating over an array list versus iterating over a linked list? Well, the array list is going to be stored contiguously. So the first time we access any index of the array, it's probably stored in RAM. I'm going to drive my car out there. I'm going to see that I'm accessing a single index of an array. I'm going to be like, oh, I might as well take the whole thing. I take the whole thing as close in to the CPU as I can get. And then if I'm using those indices of an array, every time something new gets added, it's like, whoa, are you still using that array? Keep it around. It's got one more where in it. So that is the real reason that the array iteration runs so much faster than the linked iteration, because not only do I not have to jump around within memory, but I don't have to necessarily jump between rungs of memory. In fact, there are situations where in the linked list, one of those nodes is in L1 cache and one of the nodes is all the way out to RAM. Imagine the difference between walking to your refrigerator versus driving out to the store just to get between one node to the next. And so here, taking us back to the very first slide that we looked at today, remember, it is an array of arrays. I love the drawer analogy. So the reason sum1 runs so much faster than sum2 is when I access 0, 0, I jump into this index of the array, and then I jump into this index of the array, and the computer grabs this entire array and brings it as close to the CPU as possible. So if I go index 0, then 0, 1, then 0, 2, I'm leveraging all of the memory optimizations that come with using arrays, both spatial and temporal, because the computer is going to treat this as a separate array from this one. So imagine if I pulled out the drawer and I looked at the first shirt, and then I pulled out the second drawer and I looked at the first shirt and that, and then I pulled out the third drawer and the first shirt and that. By the time I have done that, the computer has probably jettisoned this array all the way back out to RAM. So I want to deal with everything within the most localized array at one time, so I get those memory boosts. Questions? Okay, amazing. Then come back on Wednesday. We are going to talk about parallelism and threading, which is the one thing different between this version of this class and the majors only versions of the class. Except I'm going to do it in one day instead of 2 weeks. We'll see how that goes.